Did you unmute this? Did you unmute? So shall we? So hello, welcome after the coffee. And our next speaker is Genadi Levin, who will tell us about an interesting formula regarding the multipliers for the rational map, I think. Yeah.
I would like to thank the organizers for the invitation and opportunity to talk. Yes, I think the formula is interesting, but not new. Profit more than 10 years ago. I wanted to talk about some applications of this formula. But first, I'll start with. Let me start with general result about spaces of rational maps. Also, not new. So let's consider rational map of degree D. Okay. And the question is, what is the natural space, local space around F to consider? An answer kind of known. So assume that F has new different critical points with multiplicities. Okay, so then the sum of these multiplicities has to be this to d minus 2. And let's consider, well, I mean, all this rational functions consider any rational function degree considers as a point in the complex projective space of degree, I think. And so let's consider rational functions close in a neighborhood of the set. So such that any G from this neighborhood has the same number of different critical points with precisely the same multiplicities. Okay. And consider the following map. Here I write all images of these critical points. Okay, they can be occasionally the same. I mean, they don't have to be pairwise different. And kind of classical result is that this space of maps like this is embedded here complex manifold of dimension nu plus 3, and this vector is a part of local coordinates, so it can be completed by 3 more local coordinates to form the coordinate on this manifold. Okay. this is okay. Well, let's some notation. So that will be this space of maps G, like this, with the same this and the same this. And one can consider also if we start with a polynomial, then one can consider finite, critical points on the complex plane and monic centered polynomials. And then this vector will be complete coordinated. Dimension will be just new. Okay, so there is a short elementary proof of this fact in paper with Shen and Van Strien. And classical proofs use okay. Now the formula. Let me consider some special normalization of F from the beginning. So kind of subspace of this. No, just some special normalization. So one can always assume by a Möbius change of coordinate that infinity is a fixed point. Okay. This is complex number, not zero, because one can always, in fact, one can always assume that it is like this, or because any rational map has either Abelian fixed point or fixed point with multiplier 1. Okay. And then the local space, let's consider locally maps only like this, if some close to this. Okay. And then the same vector with just two coordinates. Two more coordinates will be a complete list of coordinates in this manifold. Also manifold of dimension, in this case, new plus 2, because we fixed them infinity. Okay, so I will consider this space with such normalization. Or just monic space of monic centered polynomials. Okay. Now, so we have F like this. Let's consider so-called operator. Ruelle considered such operator with transfer operator with complex weights. So it associated to F, it acts on functions like this. This is it appears in Thurston study of critically finite maps too as a push-forward operator. In also in other problems in dynamics. So these are all pre-images of that. I assume that is not a critical value. Okay, so this is this operator. It has Thurston discovered, I mean, that it is kind of contracting because if you have some set V, which is backward invariant, and if you have a fixed point of this operator, then and this fixed point is integrable, Lebesgue integrable on this set complex in Riemann sphere, then just by the change of variable, you get this V. And then we change variable here and pass modulus inside, and you get this. Okay, and because of this property, it usually just means that psi is 0. So this is a fundamental property, but it holds only if psi is integrable fixed point. We will see now that there can be many non-integrable fixed points on this operator. Okay, so let's so we have f, we have this operator, and let's now consider I know. Okay, now let O be any periodic orbit of F of exact period M. And rho is a multiplier. Okay. This orbit. Let me assume, although it can be relaxed, let me assume that this multiplier is not 1, and not 0. But again, it can be considered this case as 2 on some assumption. Okay, then because it is not 1, this periodic orbit moves holomorphically when map changes in this space. Okay, so we have, and let's consider rho as a function of critical values. Okay. So we have a holomorphic function of these variables. Okay, and now let's associate to this periodic orbit a rational function. I know that I offend people by talking that operator acts on function, not a quadratic differential. I just don't care. Okay, about such. Okay, so let's consider this rational function. That's an explicit rational function associated to this periodic orbit. So the double poles and points. By the way, these numbers No, it's not enough. Divide this by rho over my 1 minus rho. And in fact, this number has a clear geometric meaning. It's related to uniformization around this, say, if you consider it hyperbolic. So modulus rho is not 1 and not 0, then this second derivative of the this uniformization, Koenig's uniformization function normalizes that. If you normalize, so that then this will be precisely second derivative. Okay. And now that's it. And now the formula is the following. And the formula is this. A minus TA is equal to sum okay, so this precise relation. So this derivatives in the parameter in this space of functions. Let me assume that no critical value is infinity. If it is infinity, then it is omitted. Okay, so this is. And for polynomial, point central polynomials, this is exactly the same form. Then this is automatic. Okay. For unique critical map family, one can prove it by brutal force, by just calculations. I mean, if you know what to prove. But for in this general form, there is another proof, mainly not calculated. Okay. So let me consider. Well, it follows from here, for example, that if this gradient, no, it's not also true. 1 over rho it should be. So it is because I wrote rho here. Okay, this is the formula. Okay, so it follows some, in particular, if this gradient is 0, this is gradient. Is 0. So if it is if and only if A is a fixed point of T. Okay, so there could be many of them. Although this is not an integrable fixed point because it has double poles at the points there of the periodic order, so it's not, it's permitted. Okay. But there is one case when one can easily find forward invariant open set away from this orbit. So like first simple application, let us assume that rho is the periodic orbit is attraction. Okay. Then you can just take small neighborhood of this periodic orbit and take it away from the complex plane. Infinity in principle is also kind of problem because of that, but there it is almost integrable, so it's not a problem. But in this case also neighborhoods of poles can be removed, and the rest is backward invariant. And then you immediately get that the gradient cannot be zero. Okay. And in this way, one can get the following result that so assume that F has R periodic orbits like this. So assume that there are R periodic orbits with multipliers such that modulus rho I is less than or equal to 1, bigger than 0, and not. Okay. I mean, modulus 1 is okay. In fact, these cases can be included too. For example, this case, 0 can be included on the additional assumption that there is only, what does it mean 0? That there is a critical point in this orbit. Assumption is that there is only one critical point. Okay, and this case also can be included, one, assuming that it is not degenerate. So the second derivative is not 0. Okay, then so. Okay, so and what is then these multipliers are local parameters. Meaning that in the whole list of coordinates critical, in fact, not only in the critical values, you can replace R critical values by R multipliers. Okay, so if there is a maximal number of periodic orbits like this, then they are just parameters, complete parameters. Okay, this is all. I mean, it's not so immediately. This is immediate. This is not so. Okay. Another, I mean, okay. So other application is a simple application. Is about something that, I mean, in non-trivial cases should not exist. I mean, invariant light. So assume that F has an invariant line field on the Riemann sphere. So there is which is not 0 on some invariant set E of positive measure. Okay, which is this the fixed point of operator which acts on such coefficients. Well, so invariant means that it is a fixed point. Well, conjecturally, except for very rare explicit cases, there are no such functions on the supported on the Julia set. But okay. And then integrate this identity against this invariant line field. Why I wrote T star? Because it is in fact a joint operator to T when we consider acting on because dx dy this is just again change of variable. Okay. And then multiply by mu, fixed point of this, and then we cannot integrate because A is not integrable. But let's do the following. Let's consider a small neighborhood of one of this point of the side of the periodic orbit of one R, and pull back of this along the cycle, okay, and take it away. And also one should deal with infinity, but let's ignore this. So okay. Well, this is corresponding to this periodic order. Then one can integrate, and when you use this formula, which in fact means that if it is mu, then this is just this because it's fixed point. Okay, and this will be A. Okay, but V will be this. And this is integrable. Infinity. And then when you one can send R to 0 and get the following. And get this because when you consider this, if this is V, F minus 1 pre-image of V will be partly contained in V because rho is repelling fixed point. I assume for here that O is repelling fixed point, so modulus rho is bigger than 1. And then you get some fundamental domain around point B1, and when if R tends to 0, you get this formula. One. And here limits along, I mean, we take fundamental domain. And send it to 10 to B1. And this is equal this. This is the formula. In fact, this is kind of, okay. Well, I mean, one can prove something like this without this global formula, but just looking at variant Beltrami coefficient locally, and then here you get the speed of the multiplier with respect to the parameter. I mean, anyway, I mean that's not unexpected something. I mean, at least locally. But I want to use it somehow. Let's consider a particular case. Example. Plus B. And let's assume that the Mandelbrot set has a non-hyperbolic component, Q component. Okay, so this is non-hyperbolic component. So V is here, and assume that V is here. Then it's Maness-Sullivan that then F carries an invariant line field on its Julia set. Okay, so this is 1 almost everywhere on the Julia set. The Julia set has positive area, and it is 0 outside. Then this number, the kind of calculation is the following. So -1 over rho in this integral is equal to the conformal radius of f of w at the point V, just precisely. Okay. For example, unavoidably, if V tends to the boundary, then this has to tend to 0. These are calculations using some standard formulas from quasi-conformal maps. Okay. No, of course I assume this. here I don't assume that the modulus nu is 1. So it has geometric complexity of the Julia set, which probably doesn't exist. Okay, but okay, so let's assume that it exists. I want to say something about application of this formula to stable, structurally stable maps. Okay. So let's assume that let's consider polynomial space of monic-centered polynomials. So F is a monic-centered polynomials. And corresponding local space with critical values as local coordinates. So and assume that F is structurally or topologically this is the same, stable. So for every there is a neighborhood in our space such that F and G are topologically conjugate. Okay. But then by the theory, okay, but then by the then it means that the Julia set there is a holomorphic motion that moves the Julia set in this neighborhood. Okay, and then so and this well, more specifically, let's move F not just in some direction, but in a direct. So there are local coordinates. So let's fix all coordinates except say first one. So we consider. So these are critical values corresponding to F, and I consider this subspace. I can do it because this is coordinates. Okay? And then if we move F structurally stable in this surface with just one coordinate, then there is holomorphic motion, and there is a family of invariant line fields, okay, which depends only on one coordinate. And then holomorphically depends. So it will be something. Let's something. Plus high order terms. Okay, so I stress that it depends only, everything depends only on V1. Okay, and then It is also well known. This first of all by the Teichmuller theory of rational maps. Structurally or topologically stable is equivalent to quasi-conformally stable. Okay, so there is the family of quasi-conformal maps, and this is Beltrami coefficient of such map. I mean, at the parameter v1, and it is invariant, and then one can see that this is also invariant. And normalize the quasi-conformal maps at infinity like z plus this, because it is conformal near infinity. You can do this. And then also kind of also known formula is the following. Then the derivative of this with respect to parameter, okay, the derivative of this, sorry. Is equal to this. Mu. Okay, and in such a way we identify the meaning, the formula that I raised of these functions 1 over z minus v1. Okay, but on the other hand, this, for example, if we can see, sorry, v1. Only at v1. If we consider this at some omega, then it should be omega. Okay, but this map says v0 1 to v1, so the partial derivative is just 1, and then we identify like this, and all other critical values along all other critical values they are just constant, so the derivative will be 0. And then we get the following. That assuming that f is stable, so that for every I, there is we move still in v1 direction, but we can move in every v of the I direction. There is some function such that this way, this is as I told, it is 1 if omega is v1 and 0 at v2 and so. Okay, and then we get this. Just I. Okay, but now one can, if we put modulus here, and then write an equality with modulus here, then you just calculate it and get the following bound for the speed of the multipliers, assuming that polynomial is stable. So there is some C depending on stable polynomial, so that for every periodic orbit as above, for its multiplier, okay, so only through the speed of the multiplier, only through the multiplier itself, okay? So otherwise it's not true. Where C is just sum of the norms in infinity of this function. Okay.
Excuse me, I'm a bit confused about the statement. What does for any O means?
So we have stable polynomial, and then there is C, so that for any all periodic orbits are hyperbolic. So for any periodic orbit, it's a function of these critical values. You have this inequality.
So for any periodic orbit of the polynomial.
Of the polynomial, or individual polynomial, yes.
So the C depends on the polynomial? Oh, I see. Thank
Well,
you.
I mean, C is this.
Okay.
So of course, it's crucial that it is dependent on no. Otherwise, it doesn't matter. Okay. Now, how much time? 2 minutes. Then I'm in trouble. Anyway, so conjecturally, density of hyperbolicity conjecture that says that any structurally stable polynomial is hyperbolic. Okay, and then a stronger conjecture says that F carries no invariant line field on the Julia set. Now there is kind of meta thing that says that once F has complex bounds, whatever it means, from it's at the infinite sequence of levels, then F there is no invariant line. Okay, now there are two cases to consider. F is finitely renormalized. Then Kozlovsky and Van Strien proved that the complex bounds exist. Based on previous work by Shen, Kozlovsky, Shen, Van Strien, and on Kahn, Levich, Lem. So always is. So it means that for finite renormalizable polynomials, no invariant factors. Okay. Now, but still, there is case of infinite renormalizable polynomials, and then again, if complex bounds exist from time to time, I mean, but at some sequence of levels, then no invariant line fluid. And there are many classes of polynomials, mainly quadratic, but not only infinitely normalizable with complex bounds, but it turns out that the property of having complex bounds, it's very fragile property, and we proved recently with Bloch, Overstegen, and Timorin that whenever there is renormalization with satellite renormalization, with such that there is a base cycle here, say 2 cycle, okay, and to each point of this 2 cycle attached s small Julia set in this orbit, okay, and then we proved that I think an amazing bound that for any choice of fundamental annulus of the renormalization, and the result is more stronger, that the modulus of this fundamental annulus is bounded by just number which depends only on the relative period S and independently on this is the one. Independent is for any rational function. It means that it's extremely easy to destroy complex bounds. Just put this satellite renormalizations and that's it. Okay. Okay. So and then I don't have time to give some very strong condition as an application of this formula. Okay, let me maybe just state the result, and it's not a result, but mistake. For maps without, not assuming complex bound. So this is result. So it's not written down. So assume that f is stable and infinitely renormalizable. Infinitely renormalizable means that there is a nested sequence of polynomial-like cycles like this. Not necessarily satellite, just okay. So and assume that and let OI be a sequence of periodic orbits, which so that they belong to different renormalizations, orbits of some renormalization, and they are nested. Okay, and this is the period of this orbit and multiplier. They are all repelling. Okay, now and then assuming f is stable, then sup of has to be 0. It's a very strong condition, but on the other hand, one can write even combinatorial condition that, no, I mean, this is not very strong. One moment. So it means that if lim sup is positive, then f is unstable. And it's a strong condition that this lim sup is positive, but one can, anyway, this is not empty, and one can write combinatorial condition on rotation numbers of separating, dividing fixed point easily, right? And that guarantees that lim sup. And the proof heavily uses this formula. And let, because again, I want to draw a picture, which again is known, but maybe not as a picture, but something else. So except for the, so this formula is heavily used, and this lemma that I raised. But and another simple fact: assume that you have two maps which are quasi. Okay. Just picture, nice picture. So, so assume that these two maps are K quasi-conformally conjugate. Okay. And then there is, of course, so there is a relation between rho and lambda in this case, and the relation is this following. So there is a log rho, okay, u plus iv. So this is v, this is u, and let's draw the following circle. So this is u, write u over k, and here u multiplied by k. K is bigger than, or maybe 1, okay? And then draw a circle here as a diameter. And then the claim is that log lambda must belong to this circle. Okay. There is, it's, I mean, one can write down just quasi-conformal map with minimal dilatation, okay, like that, and check in principle. But that's that. But I'm not aware of such explicit picture. Okay, and to prove here, I use this formula, and then, but this formula gives some specific constant, and one should kill this constant, and then for this pass to renormalization, and then there is a problem of relation between multipliers of cycle and multipliers of straightening map after renormalization, and this is the relation. Okay.
Any questions, comments?
About the last theorem, do you need to assume the stability of f in the whole parameter space or just in one-dimensional slice?
No, in whole, in this in the space that I introduced in the beginning.
Okay, so
of course, if it has one critical point, then this is the whole.
So stability just in one-dimensional slice is not sufficient for the method.
No, because I need to estimate all partial derivatives on all vi and not only one. No, okay. Maybe it's not. I don't know how to prove.
Okay, yeah, thank you.
Artyom, I think you had a question.
Curious. So there you have a bound to pi over log s over 34.
Yes, long, of course, natural.
Mm-hmm. But 34, where does it come from? Is there some reason?
It's magic.
It's not a prime number. I don't know. Well, I can tell how to prove this. The crucial thing to prove this formula is to consider, even in the polynomial case, Riemann metric on this Riemann sphere. Okay, and then if we consider this satellite orbit, Then the problem with Euclidean metric, then the sizes of different small Julia set can be very different. But on the Riemann sphere, you can always kind of make the size such that it is big and the complement is big in the Riemann metric. And then by calculations and cross rations, if I mean, I'm not sure it's a precise number, maybe 33.5, I don't know. But, doesn't have any.
Any more questions, comments? As always, from our participants online, please don't hesitate and just unmute and talk to us. If not, let us thank the speaker again. And let us meet in 5 minutes, so 12:25.